Okay, we continue to lecture chapter 4, part 2. Okay. Um, okay. So, have you have learned that actually in Laplace transform, we involve sometimes initial value. Okay, initial value is that the value that is already there, that and actually you can use this value to solve your given problems. Okay. So initial value volume, we define the initial value of ft as f0 plus as the limit of t approaches 0 from the right. Okay. So if you have, this is a positive region, right, and this one is negative region. Okay. So approaches from infinity. Okay, infinity is here, approaches from the right going to here. Okay, because you have also negative infinity here, right? But we are discussing about from here until approaching to the from the right to the left. Okay, so this is um, the initial value. Okay, as the limit approach 0 from the right. Okay, so the initial value property allow us to find f0 plus. Okay, if you see here is in time domain directly from your fs without first finding the inverse transform. Okay, so you will solve this you will solve the in Laplace domain, okay, with given initial value, okay, like this f small f 0 plus, okay, without you actually need to do the inverse transform in the first place. You do Laplace transform first, you solve, and then later on you convert back to the t. Okay, so initial value theorem is defined as, you see here, this is a Laplace with a function of time here, Laplace transform of this as the limit approaches 0, approaches 0 from infinity in time domain. In s domain it will be infinity, so it vice versa. It's like in t is when it is approached to 0, but in Laplace transform it is s approach infinity. Okay, you can see the difference. Make sure don't just read, I mean, recklessly focus what on the writing here. Okay, so in time domain is approach 0, but in Laplace is approach infinity. Okay, and then you can see here, in order to have your time domain signal back is f0 plus, and then as the limit of s approaches infinity and s fs. Okay. Okay. To prove this property, consider Laplace transform of derivative. Okay. You can refer to your appendix as well. I'm not sure how you're going to divide the screen, but sometimes we need to refer to the appendix. Okay. Okay, to prove the property, consider Laplace transform of derivative of ft. Okay, so you have this Laplace transform of the derivative. Okay, derivative, and then you perform this transformation, right? This one is actually the transformation, Laplace transform. Okay, where from 0 until infinity, am I correct? And then you have e negative st. Okay, and because this is first order equation, I mean first order, which is this, you can convert to this. Okay, for based on the table. I think you already seen the table, right? Then you see here, this is actually your initial value. Okay, initial value where you can actually you can put later on. Okay, depend on the question. Okay, take the limit of this relation as s approach infinity, because in time domain, okay, when it is approach to 0, in Laplace transform it is approach to infinity. Okay, they are like pairs. Okay, and then for s real and need to be positive. Okay, so you can see the limit, okay, from s approaches to infinity in the Laplace domain, and you have dft over dt. Okay, e negative s. Okay, and then you see here limit as s approach infinity. Okay, okay, 0. Okay, this one is s is approach infinity. Is because you see here is s approach infinity, what happened? E negative infinity, right here. Mm, how I'm going to show this? Okay, so you have E approach S approach infinity. Okay, so because this is like this, if you want to convert into, it is actually like this, right? Am I correct? It's like this. So if you notice, if this is infinity, okay, 1 over infinity is 0, right? 1 over infinity is 0. Okay, this why you have 0 here. Okay, can FO plus and then limit, we need to know the value of limit in order to find the initial value. Okay, here we need to know the value of limit ft in order to find initial value. Okay, so this one is in the given problem, it will show for example f0, what is the value. Okay, you just need to plug in later on. Okay, so for example one, okay, find the initial value. Okay, find the initial value of t approaches 0. Okay, for ft negative for ft 3t square plus 4t plus 3. Okay, so this one you can use directly from the table. Okay, this one is actually shown by the factorial. Okay, where is the table? Here. Okay, tut. Okay, tut, and then it's a factorial. If it's t square, it means 2 factorial over s 2 plus 1 is actually 3, so 2 factorial over s3. Okay, something like that. Okay. So that's why you have this from the table. Okay, then f0 is when limit of s approaches your infinity. Okay, you have this, then you just approach to infinity. Okay, 6 over s infinity is 0, right? 4 over infinity is 0, so that's why you end up with only having 3. Okay, so now this is final value theorem. Okay, just now is initial value theorem, so it's different. Eh, okay, so allow us to compute the limit of the signal as ft. Okay, as t approaches your infinity. Okay, from its Laplace transform as follows. So now t approaches infinity. You see here, t is approaches infinity, not t approaches 0. Okay, because it's final value theorem. Just now is initial value theorem. Okay, initial value. Now final value. So final value as if it's going toward here. Okay, going to here. So means towards the limit of infinity as final, right? So this one is initial, so it's not the same. Okay, this one is initial, this one is like final. Okay, so you have t approach to infinity is equivalent to, okay, now when t is approaching infinity, the Laplace will be approaching 0. Okay, they just like convert vice versa to one another. Okay, so then f infinity, okay, for final value is limit t approaches infinity of your ft is actually equals to limit of s approaches 0 sfs. Okay, you see here sfs. Okay, not fs only, but there is s there. Okay, and then useful in some application. Okay, never mind. Some function does not have a limit as t approaches infinity, hence important to know that the limit exists before applying final theorem value. Okay, so some they don't put limit, so you need to they don't they didn't put limit as t approaches infinity. Okay, so you need to know that the limit exists. Okay, and then actually you also need to know whether this one is actually given with initial value or actually with final value theorem. Okay, final value. Okay, so example 2. Okay, given gs equals to 2s over whatever is this. Okay, calculate the final value of gt. Okay, so it's given us the Laplace transform equation. Okay, and then we want us to solve for gt. Okay, solution by employing Laplace transform final value theorem. Okay, see here, g infinity. Okay, g infinity is actually limit t approaches infinity, but in s domain it will be approach to 0. Okay, and you see here there is a s here. Okay, Make sure you don't miss out this S. And then limit of S, then you put this value to S plus 2, whatever inside. Okay. And as S approaches to 0, okay, as S approaches to 0, so you have your S 0, 0, 0. So you have 2, 2, 3, 3, and 4. Okay. Wait for one. Okay. So in the circuit analysis, the standard one, you have resistor, inductor, and capacitor. This one is very basic, very basic components. Okay. So the differential and integral. Now we have differential and we also have integral. Okay, properties of Laplace transform if used to solve circuit that is transformed into S domain. So if you see from your again from your appendix, you need to check. Okay, this one is integration. This one is differentiation. If differentiation, we already see just now few example, few exercise, and then integration is this. Okay, integration is from 0 until tau, 0 until t, with f tau and d tau. Okay, so when we want to change to Laplace domain, we will have fs over your s. Okay. Okay, so this is circuit analysis in case of this the component is a resistor. Okay, if a component is resistor, so you have your vt. Okay, vt and small I passing through your resistor. Okay, and if you convert to time domain, Laplace domain is just Fs Is over R. ISR. So for resistor is straightforward. So resistor nothing to be seems like difficult. This one is just like the resistor. Okay, it's a value. It's a bit different if it's a capacitor and inductor. Okay. Now we see from the inductor view, okay, inductors, you have a Vt equals to L di over dt. I'm not sure where you learn this. I mean, I'm not sure if you have learned this. I think in circuit theory. Is it correct? I think you learned this in circuit theory. I hope. I'm not sure. But you need to learn this from somewhere. Okay. From some course of electrical course. Vt for inductor, okay, is actually L di per dt. Okay, maybe you learn this in circuit theory, right? I'm not sure. Okay, uh, and then if you want to convert to your equivalent circuit, you have two choices in Laplace domain, whether you can have a series connection or you can have a parallel connection. Depends on your question, which one is more convenient to you. Okay, you can use either one, but of course in solving, you will in solving equation solution, you will know which one is better than the other. Okay, so you see you have vs slis here. Okay, with Li 0. Okay, this one is like a voltage drop. This one is also, I mean, this is a voltage, but it's just like combined, they will contribute to your Vs. Okay, so this one is SL. Okay, SL I, because this is here, di over dt. And then because you see here, this one is actually a differential. So you're going to have uh, this one, you have this one, right? You have initial value and this. Okay, so this is the initial value, the initial value. Okay, this one here, the table, the IDT. This one you have until here. Okay, this one you have until this part. Okay. For circuit analysis for the capacitors, okay, for the capacitors, uh, this one also I believe you learn. Not sure you learn also where, but you should learn this before this class. I think circuit theory as well. So VT of 1 over C IT dt. Okay, so this is capacitors. So 1 over C is like constant. C is like constant. Then you have a function here, but if you see the integration here, okay, it's actually when you convert, it's actually fs over s. So you will have, that's why the integration part you will have 1 over sc. Okay, you have 1 over sc. C is just the constant, and then you have the initial value. Okay, then you have the initial value, which is v naught over s. Okay, similarly, okay, time domain, this is for capacitors. Okay, you can solve whether it is in a series connection or parallel connection. Okay, you can choose which one. Okay, so for vs here is 1 over sc with is, and then this one is the v naught over s. Okay, so this is the series connection, and this is the parallel connection. uh, Equivalent circuit in Laplace domain of our time domain. Okay, equivalent. Mm. Okay, find it where when the switch is closed at t greater than not sure. I want to see whether I have time or not. To Oh, okay, okay, I think I have time. Okay, so this one I take from Google. I take from Google. You guys can put at your own slide. Depend on you. But I think you, if you, yeah, because I'm not sure you guys know not partial fraction. That's why I put this at my slide. Okay, but you didn't have this because I just put it. Okay, so find it when the switch S is closed as t greater than 0. Second in the circuit below with the assumption that the value of the initial current this. Okay, so I'm changing screen. Okay, I'm changing screen. mm, Wait. So refer to that example because I'm going to show some working. Wait. Need to Okay, so you refer to your lecture slide. Okay, while I'm showing this because I cannot show in many things. Okay, wait. Okay, so given the circuits, after when it is after t0, the switch will be closed. Means the circuit will be complete. The circuit will be complete. Okay, so the circuit will be complete. Okay, so this is actually you have a plus minus. Okay, this one is actually 3 ut. Okay, unit step 3 ut for your voltage source. Okay, and then you will have your, here is 2h. Okay, why it look like a bit blur? Oh, okay, no wonder. Okay, so and then you have your, here is 4 ohm. Okay, 4 ohm. Okay, so you need to refer back to your inductor. Okay, to your inductor, what is the equivalent form for inductor? Because now it's inductor, right? So you want to change this chair, you want to change this one. Okay, to your Laplace domain now, of course. Okay, so wait. Okay, so here, okay, this is the circuit with 3 ut, and then Laplace transform. If you choose parallel series connection, you will have like this, and so you have your friend here, negative infinity, negative and positive. Okay, and then you have your Li, initial condition. Okay, and then you have this is SL. Okay, this one is SL. Okay, and then you will have the resistor. Okay, so resistor, this one is unit step. Okay, if now we need to change this one to Laplace transform. I mean in the Laplace domain. Okay, so it should be in S. So for unit step, what is the unit step? Unit step in the Laplace. Okay, you can go to your appendix, right? So this one is 3u, but in Laplace transform, I mean in Laplace transform, it will be 3 over S. Okay, 3 over S. Okay, and then for the resistor, okay, for the resistor you have 4, right? 4 means we have a value. Okay, we have value. So in Laplace transform, what is it? Okay, in Laplace transform, what is it? Okay, because this is just a number. This is just a number. So then you have a current. Okay, you have a current. Okay, and this is 4. Okay, so the question is asking, what is the question is asking, find IT. So you solve in time Laplace main, then you will okay, here IT. Okay, it wants this, but you settle for IS first. Okay, then you will obtain the IT again. Okay, with this is inverse Laplace. Okay, so okay, now we do the voltage. We do the voltage, total voltage in the circuits. Because you see this one is 3 over S, and this one is Li naught. Okay, Li naught. Okay, you do the equation, equivalent to the voltage. Okay, I think you learn this, what we call this KVL. Not sure you learned this before. Okay, you have KVL, Kirchhoff voltage law, and then you also have Kirchhoff's current law. Okay, you see here is two. Okay, first is actually you get here is actually you see this is the direction. Okay, the direction. So seems like contradict with your 3. So that's why it's negative 3 over S. Okay, voltage. And then plus with SL. Okay, SL is what? SL is refer to the slide. Okay, refer to the slide is actually uh, SL plus SLIS. Okay, um, plus S. Okay, SLIS. Okay, and then minus Li0. Okay, initial conditions. Okay, so this is actually to obtain the voltage. Okay, and then you have 4. Okay, then you have 4. Okay, you have 4 because you have another, don't forget the resistor. This one is actually represented by your inductor. Okay, then you have another which is from the resistor for Is. Okay, equals to 0. Okay, mm, okay, and then Li, what is the question just now? I mean, what? Okay, so it's give us the value of the I naught. Okay, it give us the value of I, the small I. It give us the value of the small I. Okay, small I, which at initial value is equals to 5. Okay, so this 5, if you do the into the Laplace transform, what value that you get? What value do you get? Is 5, right? So 93 over S plus L. SL, you already know what is your L. Your L is what? Your L is 2. And then IS you didn't know, but you actually, at least you know that is actually 2 SIS. Okay, this one is initial value. So you know that your L is actually 2 and initial condition is 5. So at negative 2 times 5, you have negative 10. Okay, and then you have 4 plus IS. Okay, sorry, 4 IS. Okay, then you do the factorization. Okay, you do the, I mean, rearranging. Rearranging. Okay, you will have 3 plus 10s. Okay, over s 2s plus 4. Okay, 2s plus 4. Okay, s 2s plus 4. Okay, and then you can do with your partial fraction. Okay, you can do with your partial fraction. Okay, so partial fraction is easy. You will change s equals to what? That will cause the whole term involving a is 0, so that you can settle, you can solve what is the value for b. And then the next is you change the value of s if s is what, in order to make the product, the term that involving b is 0, so that you can solve for a. Okay, am I correct? So this one is mathematics. This one is mathematics. I don't want to really touch mathematics. 3 plus 10s. Okay, then you will have a 2s plus 4. Okay, and then you will have plus bs. Okay, you will get, right, you will get the value of I in terms of Laplace transform. Okay, and then you will once you have your is, you will then convert it back to the time domain by inverse Laplace transform. Okay, so you will get answer, uh, you will get the answer. Okay, but remember, in time domain later on, you need to remember, you need to include ut. Okay, Laplace, because Laplace is actually from 0 until infinity, means positive value. Okay, not the negative one. Okay, so I'm not sure if I share to you guys this the answer, the did I share this one? Because it should be in the slide, but maybe I forget this one, because when I refer to, do you have this in your slide? Do you have this in your slide? You have or not? Because we have syllabus to cover and things. Maybe when I'm transferring into my slide and using my own slide, I think I left this information. Am I correct? Do you guys have this information? So wait. Wait for a while. Wait. Wait. We have actually the option of having standard slide in order to, so one lecturer will not, all lecturer will teach what should be covered, but we can add our own extra information. Okay, that's why maybe you compare with your class, different class, maybe different section, they might have a bit similar slide, because we need to have a bit similar slide minimum, then we can add our own information so that all section will have the same learning. That's why. But that's why when I'm transferring to my own slide, I forget the information just now. I forget to put, and I know I forget to put it. That's why I just want to have confirmation. That's why I'm asking you guys just now. Wait, Mm-mm. I will put into our WhatsApp group. Wait for a while. Chapter internet a bit slow, because I put all at Google Drive. So when I open, that's why it's really depend on internet. Mm, which one I left? This one. Uh, I need to give to okay session. Very slow. So do you guys get it? Do you guys get the solution? Do you guys get the solution? Do you guys get the solution in the WhatsApp? Do you guys get it? Okay. So with that, you guys can try first, huh? Don't really. Okay, you guys try first, then you refer back to your answer whether you answer it you whether you do it correctly or not. Okay, don't just depend on the you do first. Okay, it will be better for that way. You do first and then double check whether you answer it correctly or not. Okay, so I leave you guys. Wait, I wait for a while. Check. Okay, quiz 3 will be postponed until on the 18th. Okay, on the 18th, because I bit busy lately. I was, and then also your friend has flight. So I not yet set the question. Okay. Mm, wait for a while. I want to see tutorial for what you can do. Okay, I mean after this lecture. Okay, where is the question? Wait. So so let we see what actually you can do after chapter. Okay, what question you can do? Oh, actually you can do everything. Okay, so okay. Please do question 3. This one of course is for the next tutorial. For the next tutorial, chapter question 3 until this one can be done. You can done it all of this. Question 3 until question 6. So our next tutorial, our next lecture will be a 2-hour tutorial, because you see there's a lot of question, right? So question 3 until 6. Okay, question 3 until 6. Okay, you guys can do at your own leisure. Okay, next 2-hour tutorial we will have this question to discuss. Okay. Okay, you guys